Okay. I guess we are live now. Okay. So, welcome everyone, and thanks for joining our first online event. I'll start by presenting ourselves. We are Deep Learning Portugal, a group of volunteers dedicated to share insights on deep learning inside and outside Portugal. The meetup of today. In the meetup of today, we'll have a 45 minutes of talk, and then we'll have 10 to 15 minutes of Q&A to Diogo. To all the viewers, feel free to add your questions to our YouTube chat, because we will be looking at them, so feel free to give your contribution. And so, going for the presentation of our speaker of today, Diogo Pernes, is a senior research scientist at Priberam and is also serving as an invited assistant professor at University of Porto. And today we will have him talk about abstractive summarization, which he might introduce soon. So, without further delay, Diogo, the floor is yours.
Yeah, thank you, Manuel, for the nice introduction. Hi, everyone. I'd like to thank Deep Learning Sessions for the invitation as well, especially to Gonçalo Correia, who first sent me the invite. So in today's session, we'll talk about abstractive summarization, and with a big focus on the problem of faithfulness and factuality, which is a central problem in summarization systems. So this is a quick outline of our presentation. So we'll start with some background on summarization. We will basically discuss different kinds of summarization and how summarization, abstractive summarization, is performed in state-of-the-art models. Then we'll talk about the hallucination problem and the problem of faithfulness with respect to the source document, basically. Then we'll see how we can automatically evaluate if a summary is good or bad and why that's a difficult task. Then I will speak a little bit about my work and my approach for abstractive summarization. And hopefully at the end we'll have some time to 1 or 2 slides to speak about summarization in GPT-3 models, in particular in GPT 3.5, which is basically ChatGPT, and we'll conclude with some take-home messages and remarks. So we'll start then with some background. As I think most of you, if not all of you, know, summarization is about having some documents, some long text, and writing a new document that contains the most important parts of this original document. So in this example we see here, we see some news article about Burundi and elections in Burundi. And on the left-hand side, we have the original document, and on the right-hand side, we have an abstractive summary, which was produced by a state-of-the-art summarization system. And without further delay, we have to distinguish what the difference between extractive and abstractive summaries, and extractive and abstractive summarization. So in case of extractive summarization, which is somehow easier approach and maybe not so interesting anymore approach to summarization, in extractive summarization we are the goal is to find spans of the text or sentences that have the most important information in the original document. And when you have an extractive summary, the biggest problems that you might face are mostly fluency, because when you simply select sentences and concatenate them to generate a summary, the connection between the sentences might not be very good. So the fluency of the text might not be very good. It might not sound very natural. So it certainly does not sound like a human written summary of a document. And you might also have problems of relevance, because if your method is not very good, it might not select the sentences that are actually the most important. In abstractive summarization, we aim to generate a new text which conveys the most important information of the original document. But we can we usually do not copy any part of the source document. We write a new text from scratch. So abstractive summarization mimics what a human summarizer would do. But for this purpose, we use natural language generation models. We'll come to that shortly. But these models have problems. And in what concerns summarization, the biggest problem is factual consistency. So as we will see, often these models will produce a summary that contains information that cannot be derived directly from the source document, which is obviously a problem because we cannot say that a text summarizes another text if it has more information than the original text, or if it has information that contradicts the original text. So in abstractive summaries, you might have a problem of factual consistency, and of course of relevance as well, because it is not guaranteed that the written text will include the most important ideas of the original document. It might include information that is not so relevant and miss other important information. So how does a state-of-the-art abstractive summarizer looks like? Nowadays, all of them are transformer-based, usually with an encoder and a decoder, although there are now decoder-only models for this problem as well, but most of them are encoder-decoder. You might have heard of BART model of T5, even Pegasus. They all are encoder-decoder transformers, and if you don't know what a transformer is, we don't have time to dissect the transformer. That would certainly be the topic for a different session of deep learning sessions, if we haven't had one before about this topic. But a transformer is basically a neural network which receives as input a text and outputs another text at the output of the network, of course. And this transformer for summarization, they are self-supervised on a denoising task on a large corpus. Like you simply shuffle sentences of a document and you train the transformer to reconstruct the original document. And then they are fine-tuned in a supervised manner in a summarization dataset. So a summarization dataset is basically a set of documents where each document is paired with each respective summary. So looking a little bit more in more detail and on how this supervised training is made. So basically you have documents X. So these are the documents that you want to summarize. And for each document X, you have at least one human written summary, which I here denote by yref. And at the output of the transformer, so for each X, you will have a distribution, a probability distribution, P theta of Y given X, where Y is the random variable representing the summary, and X is your source document, and this theta represents the parameters of the neural network that you will optimize. And how do you optimize these? So they are optimized like a classification model by training it on by minimizing the cross entropy loss, or if you prefer, using the maximum likelihood criterion, which in this case is exactly the same thing. And after you train the model, you have found these parameters theta that basically maximize the probability of the correct summary given the respective document. So when you feed a new document to the model, it will output the probability distribution of possible summaries for this document. And we will see shortly how can we go from this distribution to an actual text. But to look a little bit with a little bit more detail into this distribution, how does it look like? So if we have a summary with m words, or more precisely with m tokens, which can be subwords, but we can just assume that each token is a word. If our summary Y consists of m words, so Y1, Y2, all the way up to Ym, the output of the transformer will be a probability of each word given the document and all the previous words that have been written so far. So the transformer works autoregressively, because at each time step, it outputs basically a vector that gives me the probability for all the words in my vocabulary given the source document and all the words, all the previous words in the summary. So given this vector with length equal to the vocabulary, I will have to use some strategy to choose what is the word that I will write. So what is the word that I will choose? For instance, I can choose the word with the highest probability, which is usually more or less what is done. And I take this word and I run the transformer, the decoder, only this decoder part of the transformer once again, and I get another probability for the next word given the previous word and all the previous words and the source document. And I can repeat this for as long as I want, and always adding more text to my summary in this case. So basically, we have seen how the transformer outputs this distribution, but and I gave it some intuition how can we go from the distribution to an actual text. But actually, there is no single way of doing that. That's an active area of research, by the way. But just to give you some more information about that, when we have this distribution, we have basically two families of ways of going from the distribution to an actual text. So you have deterministic approaches, which basically will look for the summary that has the highest probability, to make it simple. Actually, looking for the summary that has the highest probability is intractable. So it's a combinatorial problem with many combinations. So it's intractable. But there are heuristics that kind of look for a good summary, in the sense that a summary that might not be the most likely, so the one that has the highest probability, but is a summary that certainly has a high probability under the distribution output by the model. And basically, you have two strategies: greedy decoding, which was the one I was describing before, always choosing the word with the highest probability, and you have beam search as well, which is not so greedy as greedy decoding, but still it's a little bit greedy. And apart from these deterministic approaches, you have also sampling-based approaches, which I will not go into any detail about these, but basically, if you have a distribution, instead of looking for the highest probability, you can just generate words according to the distribution. So take into account the probabilities of each word and just randomize the sampling of these words according to the probabilities that the transformer is providing. So basically, we have these two families of approaches, but the first ones, in particular beam search, are the most widely used, at least for summarization. So putting everything together, how can we go from a document X to a generated summary Y hat? First, we feed X to our abstractive summarizer, so to our transformer encoder decoder, and we get a probability distribution, and then we use a decoding algorithm that will, using this distribution, will provide me with an actual text. So it might seem straightforward to do that, and it's not that hard. But when you look at the actual summaries, they often have problems, and the hallucination problem is probably the most common one, and also a very severe problem. So it's something that we cannot accept at all. And what is hallucination? Here we have an example. So we have some news article that describes a soldier or someone who was in a mountain or something like that, and he had an accident, and he's critically ill. he's actually in a comatose state. And when you ask, in this case, it was a BART model to summarize this document, the summary is erroneously saying that the soldier has been declared dead, which is not true. So that as far as the document says, that the soldier is not dead, so he's in a coma, but he's not dead. So it clearly, in this case, it contradicts the content of the source document. So, and when this happens, we say this is a hallucination. And note that hallucination is not only contradiction, but also any information that is in the summary that cannot be directly inferred from the source document, regardless of it being true or false, is considered a hallucination. So whenever the summary is factually inconsistent with the document, we say we have a hallucination. And note that sometimes people distinguish between hallucination or faithfulness, if you prefer, and factuality. Faithfulness basically is equivalent, is the opposite of hallucination. So a summary is faithful if all its content is coherent with the source document, and factual if the content of the summary is true. But here, for instance, when we are especially when we are summarizing news articles, we really want to be faithful, because factuality involves having some external source of information, and especially when we deal with transformers, it's very hard to control what the transformers know and what kind of external information that they can add to the document. So what we really want is that when we are summarizing, is that our summary sticks to the information that is presented to it in the source document, because facts evolve, and our transformer the knowledge of our transformer would need to evolve as well. For instance, if you have some news article about Donald Trump, and our transformer was trained 3 years ago or something, if we allow the transformer, or if we accept the transformer to have external knowledge, the transformer could say, summarizing a news article from today, could, for instance, replace Donald Trump by the President of the United States. And this information would be true like 3 years ago or 2 years ago, but certainly nowadays it's not true. So for this reason, when we have an abstractive summarization system, for instance, for news articles, we really want it to be faithful to the source document. So not to add any information that is not directly inferable from the source document. And having this capability is a central feature that we want to impose. There are two types of hallucination, or some people divide hallucination in two types, intrinsic and extrinsic. This is not the most important thing, but intrinsic basically comes from the transformer mixing things in the input. So here we have this Zach Goldsmith, and he's in a race for London mayor, but in the summary we have that Zach Goldsmith is a former London mayoral candidate, and we don't have this information anywhere. And extrinsic hallucination happens when the transformer adds information that basically comes from its pre-training. So we have here this party, UKIP, which is mentioned, but it was not even mentioned in the source document. So it just comes from background knowledge that the transformer has acquired during its training or fine-tuning, but it's not really in the source document. And when this happens, we say we have an extrinsic hallucination. For the automatic evaluation of summaries, so we want to assess if our abstractive summarization models are good or bad, and for that purpose, we want to do it in an automatic manner, of course. And a classic way of doing that is using these so-called Rouge scores, which will basically compare reference summaries with the generated summaries, and they compare them at a word level or at an n-gram level. So basically, they measure the overlap or between the generated summary and the reference summary. And of course, you can compute a precision and a recall, and then compute something like an F1 score and report this. F1 score, by the way, is the harmonic or the geometric mean of precision and recall, and you can report this as an overall measure of quality of your abstractive summarization system. But it turns out that these kind of metrics in Rouge scores have problems. For instance, here we have this reference summary, which would be the quick brown fox jumped over the lazy dog. And if the summary was the quick brown dog jumped over the lazy fox, it clearly contradicts the reference summary, so it's not factually consistent. But assuming, of course, that the reference summary is consistent with the source document, but it has a high Rouge score. However, we can have another summary that has a lower Rouge score, but is factually consistent, so it's semantically accurate. In this case, the summary would be the fast-food-colored fox hopped over the lethargic dog. So basically, we replaced some words by synonyms, and the Rouge scores became lower, but the summary is still a good summary. It's factually consistent with the source document. So Rouge scores, although they are widely used because they are both simple to implement and they are actually highly interpretable because we are just comparing text word by word, they are not very good metrics. And for this reason, other metrics have been proposed, especially for this problem of consistency. For instance, this entailment-based metric, which is called FactCC, what they do is they basically train a transformer on the task of predicting whether a summary is or is not consistent with a document. And for this, they generate a synthetic data set with factual inconsistencies. So they force these factual inconsistencies, for instance, by replacing named entities and quantities and stuff like that. And they train a transformer on this binary classification. And then you can use this as a metric or as a measure of quality of a summary. Of course, this is not perfect because the synthetic factual inconsistencies do not cover all inconsistencies that may happen in a summary. And there are these more advanced metrics, which are called Questival metric. Basically, the idea on these question answering scores is that you have your generated summary. You use a question generation model to generate questions from this summary, and of course, the answers to those questions according to the summary as well. And then you use a question answering model to answer the questions you generated using the source document. And then you compare the answers that are obtained from the summary and the answers that are obtained from the document. And if they match, then the summary is factually consistent. If they do not match, then the summary is somehow contradicting the source document, so it's not factually consistent. And there are other metrics that try to measure factual consistency. Note, however, that both of these metrics that I mentioned for factual consistency, they don't take into account the reference summaries and like Rouge scores. So for instance, to assessing relevance, they are not so good because usually reference summaries have the information that is important to assess relevance, and a summary might be factually consistent, but still miss important information. So the question now might be, how can we have improved summarization systems? So this is the pipeline of summarization that we've seen before. Here I added a final step of ranking. And what is this ranking step? So basically, when we have our decoding algorithm, we can get just one generated summary, or we can get as many as we want different generated summaries. And optionally, we can add another model that will have all these candidate summaries and try to figure out which one is the best. So the question here is, where on this pipeline, where can we intervene in order to have better summaries that are more relevant and more consistent with the source document? So it turns out that we can intervene in all these steps, and there are papers that intervene in all these steps. For instance, the papers that try to train a better transformer on the task of abstractive summarization have some papers that optimize for a metric. So instead of using only this cross entropy loss, they try to optimize the model to, in addition to minimizing this loss, maximizing some metric, for instance, maximizing Rouge scores. It might have problems, and we know that it has, but it has been done. There are also approaches that use again, these synthetic hallucinations and contrastive learning to try to penalize the model for generating factually inconsistent summaries. And there is this approach by OpenAI called reinforcement learning from human feedback, which we will hopefully see at the end how it works. It's also possible to intervene or to improve the decoding algorithm, for instance, by avoiding tokens whose probability does not change when the source document changes. So if you have a token that has a high probability regardless of the source documents that you are feeding to the transformer, probably this token is not really depending on what you are feeding to the transformer, so it's likely to be a hallucination. In a very simplified way, that's what Van der Poel et al. Did in the CPMI decoding algorithm. And finally, we have ranking approaches, which I will describe, which is basically my approach that aims again to have a metric and try to distill, to compress this metric into a reference-free function that we can use at inference time to choose the best candidate summary. So what have I done? Basically, my idea is that if I can generate multiple summaries, I would like to have a model that would be very happy if the summary is very accurate in terms of factual consistency and has all the important information from the document, and would not be happy at all if the summary contradicts the source document, and for instance, would be kind of in between these two if the summary is consistent but misses some relevant information, for instance. So I want a model that can discriminate between good and bad summaries, basically. And how can I do that? Well, I choose a metric, which can be, for instance, Rouge scores, and the metric usually takes three things, or might take three things as input: the source document, the reference summary, and the candidate. And I want to find some model that provides the same ranking as the metric would provide, but without using any reference summary. Because if I need the reference summaries, I need a summary written by a human, so I don't need the abstractive summarizer. So I want something that can find what a good summary is without looking at reference summaries. Here my measure of quality of the summaries is some gold metric phi that I have chosen, which can be Rouge scores or one of the other improved metrics that I mentioned before, or even a combination of all these metrics, like summing them or averaging them or whatever. So how do I do this? Basically, I concatenate the document and the candidate summary. I pass it through another transformer, which in this case is only the encoder. It's a BERT, and I have a scalar output. And then basically I train this model on this loss that looks very complicated, but it's actually kind of it's actually quite simple. Basically, what I'm doing is I have a list of summaries, and I want to maximize. So in this list of k summaries, if I have k summaries, I have k factorial ways of k factorial permutations of these summaries, and only one of these permutations is the correct one. So which is the one in which the best summary is the first, the second best is the second, and so on and so forth, where these first best and second best are provided by the metric phi. And basically, I want my model to maximize the likelihood of the correct permutation, which is basically what this loss is doing. And if I do that, my model will assign a low score, because I have this minus sign. It will assign a low score, which is called a low energy, to good summaries and a high energy to bad summaries. And if you look at automatic evaluation, I won't bother you much with this slide. It's kind of boring, but you see that when you compare it to BART, which is the baseline system, these EBR, energy-based re-ranking models, they consistently improve the metrics. So these are different metrics: Rouge scores, quest eval, consistency, relevance, etc. All of these are automatic metrics. And you see that these models here consistently improve at least over the baseline model. So if they improve in these metrics, then we have to check if for humans the quality improves as well. And it turns out that, for instance, in these data sets, CNN, Daily Mail, there are actually improvements. But especially when you compare in this data set, which is more abstractive, so the summaries are more different from the source document than in the CNN Daily Mail data set. When you compare with XSum, when you compare in XSum with BART and with other improved models, you see that the improvements are much smaller, and in many cases, for instance, especially here, our model is actually worse than this Cliff model, although according to the automatic metrics, it was better. So what's happening here? Well, it turns out that even the metrics fail. For instance, in this case, the metric did the consistency metric, which is an automatic metric for evaluating consistency. In this case, it did a good job. It gave a higher percentage of consistency to the bottom summary when compared to the top summary. But and so our model also assigned a lower score to the better summary than to the other one. But in other cases, this consistency metric, which was supposed to be able to discriminate well between consistent and inconsistent summaries, it fails terribly, especially when the summaries are highly abstractive, like in this case. And here, the consistency metric is actually giving a higher percentage to the summary that is not factually consistent. And because our model was trained to mimic this metric, it will also prefer this summary instead of the top one. So it turns out that the metrics to evaluate factual consistency are not as good as we thought. Although they are definitely better than root scores, they are still imperfect. So a model that is trained to mimic these metrics will also fail at the task of discriminating these consistent and inconsistent summaries. So just to finalize let's say the novelty of this presentation, or the contributions of this presentation, we'll see how summarization is likely done in ChatGPT. We actually don't know exactly how it's done there because they didn't publish any paper, and as you know, ChatGPT is not open source. But it turns out that actually OpenAI published a paper called summarization from human feedback, or improving summarization from human feedback, or something like that, in NeurIPS 2020. And it turns out that actually human feedback helps a lot. And how do they do that? So basically what they do is they use different models to and reference summaries to have, so for a document, they generate different summaries, just like I did, for instance, in my approach. And then they ask a human to rank the summaries, the two summaries, so to say which one is the best. And so the big difference, for instance, to my approach is that I was using automatic metrics and they are using actual human evaluations, which make a lot of difference. And then having these rankings provided by humans, they train a model, which they call a reward model, which is something, it's not an energy-based model unlike mine, but it's what it does is quite similar to it. So it's basically a ranking model, which given a pair of so a document with a pair of summaries will assign a score that tries to mimic the choice of a human, like saying which one is the best. So it's basically a ranking model. And they will use this ranking model as a reward model to improve the summarization system. So they will use reinforcement learning and this reward model to provide rewards to what they call their policy network, which is basically their transformer generating the summaries. And they do this iteratively. As soon as they improve the policy, they will generate more summaries. They will ask again humans to label them or to rank them. They will retrain the reward model, and they will do this in a loop. So, and the results, turn out to be quite good. For instance, these results that they provide here, which, and I believe that in ChatGPT they are even better, they show that without any fine-tuning on CNN Daily Mail, just by training the model on this data set from Reddit, they have a performance, which is this yellow line here, which is on par or almost on par with T5, which was trained in a supervised manner on this CNN Daily Mail data set. And from as far as I know, there is no systematic evaluation of ChatGPT for summarization, but the few experiments that I've done, I never saw it providing a summary that was unfaithful or that contained any hallucination with respect to the source document. So of course, as I said, there is no systematic evaluation, so you should take this information with a grain of salt. But from what I could see, ChatGPT in summarization does a really good job. Of course, it doesn't come for free, and we should understand that even this model, which is not ChatGPT, so this is the model they used in the paper of summarization using human feedback, an idea that certainly they have used in ChatGPT. But even this model that was only for summarization, it had 6.7 billion parameters, which compares with 406 million in BART large and about 800 in T5 large. So it's a huge model, much larger than any of the models that I mentioned before for summarization. So for me, it's kind of an intuitive that we need such a large model to have something that should be easier to control, like hallucinations. So it's just a matter of they basically solve the problem by scaling, and which is not feasible in many situations. And of course, this scaling is not only in terms of the number of parameters of the model, it's also in terms of the training time. It took 320 GPU days. So it's something that you certainly cannot do in a small lab or something like that. And more importantly, their training is extremely expensive because they use human annotators to provide the feedback. And I didn't find the exact amount of effort that the human annotators had, but they say that it was in the order of thousands of labor hours. So it's something that, again, is extremely expensive. And as I said before, I in this paper, of course, they have evaluation of the summaries, but I didn't see specifically in ChatGPT, as far as I know, there is no systematic evaluation of the quality of the summaries that ChatGPT provides, and no systematic comparison with other models, and in particular, no systematic evaluation of hallucinations. So I said that I never saw ChatGPT hallucinating in summarization, which is true, but it doesn't matter that it doesn't mean that it doesn't happen. So it might happen. I might have just been lucky in the few experiments that I've done of never seeing any hallucination. So now, yes, to finalize my presentation. So with a few take-home messages. So if you have a good summarization metric, if you can develop one, then the approach that I've shown you of using an energy-based model for your ranking is certainly a good choice, because it's kind of cheap to train, and you can mimic your metric in a reference-free function that you can then use to generate better abstractive summaries. The problem in this case with my approach was that current metrics are not as good as humans, and because of that, the models that you train based on these metrics also fail sometimes in very dramatic ways. And for these reasons, we can definitely see that human feedback helps. So if you replace your automatic metric by a human, then certainly it helps. And if it's more than one human, it even helps more. So if you can do that, and if you have money to do that, because it's in the end it's a question of having the money to do that, then of course that's a very good choice, as the OpenAI models show. Just a little bit more of advertising. If you are curious about more details of my paper, you can check it. It's publicly available in arXiv, and also the models and the code, we also release them publicly. You can, if you can go to this link, or you can scan this QR code, and you'll be forwarded to our GitHub repository, where you have all the information that you might need. And yeah, thank you all for attending. And just another advertisement, we have some jobs open at Priberam, so if you want to join us, you might find something interesting there for you. And now I'm open to your questions.
Hello again. Thank you very much for the presentation. Diogo, we have some questions on the comments, which I'll try to share in the recording. So yeah, I think it's working. Can you see it? From David Batista. We have, do you know about any public Portuguese datasets for summarization?
Yes, I know one. Actually, we have submitted a paper describing a dataset for cross-lingual summarization, and one of the languages included there is Portuguese. So it should be in arXiv shortly. So let's say in 2 or 3 months. So doing again some advertisement, but even excluding our dataset, which is not public yet. There are multilingual summarization datasets. One that is called MLSum. I'm not entirely sure that it has Portuguese, but I think it does. So there are datasets for Portuguese. A problem there is that, for instance, although you can fine-tune a BART to summarize in Portuguese, BART was not pre-trained in Portuguese. So if you want to have an abstractive model for summarizing in Portuguese, probably you should use some multilingual model, like, for instance, MT5, that was pre-trained in many languages, including, of course, Portuguese.
Okay, great. Then there's also another question from David, which is, do you also know about any work methods to adapt a model trained on English summarization in a way that we can apply it to Portuguese?
So that would be some kind of zero-shot summarization in Portuguese. I never saw it, but definitely I think it's possible. So when you have these multilingual models, if you fine-tune them, in a summarization in a given language, then with some effort or not with a large effort, you might hope that when you provide them with some input that is not in English, for instance, it will provide you with a summary in the other language. So in this case, in Portuguese, and it would also be interesting to research that, for instance, using task adapters and stuff like that. But this is so the research in multilingual summarization is clearly behind the research in English summarization. So it's something that is not yet at the point that it should be. So it's one of the topics actually that interests me right now is not only multilingual but also cross-lingual summarization. But replying to your question is not so. If you have a model that was trained for English, it is not, depending on the model, it might not be trivial how to adapt it for Portuguese. For instance, if the model was not pre-trained on Portuguese, you don't have any chance of adapting it to Portuguese, at least as far as I know.
Okay. David has also some feedback on the comments, so I don't know if it had something for you guys. Can you see? I guess using multilingual trained models.
Yes, like MT5, as I was saying. Yes.
Or the starting point. Then we also have a question from Jean Gant. In your perspective, what's the bottleneck to improve summarization at the moment? Bigger models, metrics, that data?
I think definitely it's not. So high quality data is one thing, because the data sets that we have for summarization are not high quality. For instance, in none of them the summaries were written with the purpose of actually being summaries. For instance, in Exxon, what they do to build a data set is they go to the BBC websites, and for each BBC article, there is a one-line description of this document, which was, of course, written by a human. But it turns out that in many cases, this one-line description of the document adds further information that is not contained in the rest of the document. So if you take it as a summary, this summary will contain hallucination. So how can you expect that your model will not hallucinate when your reference summaries do contain hallucination? So when you have trained your model to hallucinate. So having better data would definitely help. Better metrics as well, because human evaluation is extremely costly. But of course, you can always solve the problem, or at least improve it, by putting more money, which would mean a bigger model and human evaluators, like OpenAI has done. So the question is, if you don't have all these resources, how can you still build a very good summarization model? I truly believe that it's possible, and there are some very good models for summarization. Ours is not a bad model at all, although it's not perfect. But I do believe that we should, and that's something that interests me a lot, that we should be able to detect when the model is hallucinating in a more faithful way, and more precise way, without needing for scaling the model like to billions of parameters or something like that.
Okay. Great. Then we also have some questions from Augusto. Here we have, thanks, Diogo. Can you give a little bit of context on the scale of the documents that we can summarize?
Yes. So, for instance, a BART model, it has a limit of, I think, around 1,000 words. But there is research in long document summarization and also in multi-document summarization. The problem there is that actually there are many problems, but one of the problems is that you don't have many data sets for extremely long document summarization. For instance, summarizing a book, I don't think there are many data sets for that. But and the other thing is that the computational the transformer has a computational limit on the size of the input that you can feed it. Of course, you have transformers that are designed to deal better with extremely large documents. For instance, you have long former, but honestly, I don't have much experience in using those for summarization, because at Priberam, at least currently, we are mostly interested in summarizing news documents, which usually are not extremely long. So definitely long document summarization is a thing, but it's not just, you cannot expect that a model that you have trained for summarizing something that is shorter will perform very well on extremely long documents, even because computationally it's not feasible for a transformer, for a standard transformer, to handle such large documents. So for something like a news article, what I've explained here is the standard. If it's something really long, then you need other kinds of techniques.
Okay. Then also from Augusto, what exactly are the advantages of Rouge score when compared to Blue score for text summarization?
Yes. So Rouge is the most widely used for summarization. Bleu is the most widely used for machine translation. The thing about Bleu is that Bleu is only precision oriented, and Rouge takes into account both precision and recall. So that's basically the difference between those two.
Mm-hmm. All right. Then from Katerina, hi Joe, great talk. Many researchers still hold on to the CNN daily dataset for extensions. However, these have obvious biases. Can you share your, and then it continues, can you share your opinion on the quality of the summarization datasets and their impact for summarization, both for training and evaluation?
Yes. So yeah, I think I kind of replied to that before by saying that the summarization data set that we have are not very good. And this issue that Katerina mentioned is another issue that I didn't mention, but for CNN Daily Mail, that's a true thing. So for CNN Daily Mail, you get a decent summary just by selecting the first three sentences of the document. So and that's one of the criticisms of CNN Daily Mail, and one of the reasons that motivated the XSUM data set, which is much more abstractive in the sense that you cannot get these summaries by simply copying parts of the document. But on the other hand, what you get in case of XSUM are summaries that sometimes contain hallucinations. So certainly it would be very nice to have a data set with human written summaries written by professionals for the specific purpose of summarizing those documents, but it turns out that it's very hard to have these because we would need an extremely large number of documents with summaries, which simply is not available. So that's another reason for what OpenAI did for summarization. They just instead of taking the reference summaries as the goal, they said no, reference summaries are okay, but we will use humans, and the humans will decide if the reference summary is better than or not than a synthetic summary, and we will train the models to with this human feedback in a reinforcement learning setting. But of course, again, you need money for that.
Yeah, exactly. Great. And then I guess the final question from Augusto in slide 45. If you want to go there.
Okay. Yeah, but I understand the question.
Is there a point where we see the quality of the summary starting to go down again?
Okay, that's a good question. So first of all, this quality is as perceived as humans. So it might make a difference. But what I imagine here, although I didn't look at the examples that they used here, but basically here the summaries might have one or two more sentences than the shorter. So we are not talking about extremely long summaries in any case. So and the biggest problem in summarization is not when you want long summaries. It's mostly when you want to summarize long documents. So you can and from my experience, when I ask the model to provide me with a longer summary, I never saw that this would be really a problem. Usually the problems arise when you want summarize a very long document, or on the opposite, when you train the model to summarize to compress a lot the document. Because if you are training the model to compress the document a lot, then it needs to be more abstractive, so it's more prone to hallucinate than when you allow it to have more sentences, because usually then it will sometimes copy some sentences from the source document. So I don't see here that this variation in the summary log length is sufficiently large for the quality to degrade. So here, just to be more clear, I think here, as you increase the length, you are simply adding more information to the summary, so humans will perceive it as better because it has more information than the other summaries.
Okay, thank you very much. I think that's it for the Q&A session. And so thank you very much, you for your availability and presentation. I just want to inform all the participants that this video will be available on YouTube, and the slides from Diogo will be available on GitHub. We'd also like to ask to the viewers to fill our feedback form, which is going to be posted right now in the comments. And also, if you feel that you might fit as a potential speaker for our meetups, feel free to also fill the speaker application form, which will be available in the video's description. And that's it for today. Thank you very much, everyone, and especially Diogo.